some of the physical quantities have magnitude only, while others have magnitude and direction. Scalar quantity have only magnitude, while vector quantity has magnitude and direction. The aim of this experiment is to verify the parallelogram law of forces. Requirements: slotted masses, 2 pulleys, protector, ruler, pencil, drawing board, optical pins, 2 retort stands, and plain paper. Precaution: the string should be inelastic and strong. Procedure: fix the drawing board vertically by using the 2 retort stands. Attach the 2 pulleys on each 2 sides of that board. Then attach a sheet of paper on that drawing board. Suspend the mass of 40 grams of that thread and 50 grams on the other side of the thread and hang it on the 2 pulleys. Suspend 70 grams at the middle of the 2 pulleys and allow it to swim freely until when it is settled. Check by lifting both masses and see if they will settle at the same point. After seeing that it settled at the same point, mark at the corners of this one . At that point, then remove the plain paper and trace the lines on that by using a pencil. Draw the line to join the points you have marked. Call this side T1 and this side T2, and this is the original point. T1 represent 40 grams and T2 represent 50 grams. Use a suitable scale to complete the parallelogram. Say 1 centimeter to represent 5 grams. By using that scale, 40 grams will be represented by 80 centimeters and 50 grams will be represented by 10 centimeters. After completing the parallelogram, you draw the line which is diagonal from the origin point to that point. From the scale used, which was 1 centimeter, represent 5 grams, we found that on that 40 grams was represented by 8 centimeters, 50 grams represented by 10 centimeters. Using a ruler and measure this diagonal, it is found that it is diagonal is equal to 13.9 centimeters. From the scale, 13.9 centimeters times 5, this is equal to 5 take 4, this times that one is 15 and that 4 is 19, take 1, this times that one is 5 and that one is 6. Therefore, the answer is 69.5 grams. From this one, when you compare it with that one which was hanged at the center, which was 70 gram force, we found that this one is approximately, when we make it approximation, so we found that this one is almost the same as that mass which was hanged at the center. Conclusion: if two forces are represented by two adjacent sides of a parallelogram, then the diagonal of the parallelogram through the common point represents the sum of the two forces in both magnitude and direction. Question. Cite a real example where the parallelogram law of forces is applied.
Refractive index of a medium. Introduction. When light passes from one optical medium to another of different density, it changes its direction and wavelength. This phenomena is known as refraction, and the different materials which allow light to pass through have different values of refractive index. Manufacturers have to know the refractive index of glass used for making lenses of spectacles, telescopes, microscopes, cameras, and other optical instruments. The aim of this experiment is to determine the refractive index of glass. Requirements: glass block, optical pins, protractor, a white sheet of paper, ruler, drawing board, a pencil, and the drawing pins. Precaution. When drawing the outline, the glass block should not be displaced or disturbed. The pencil should be sharp. Procedure. Place a glass block flat on the sheet of paper. Attach the paper with the drawing pins. Draw an outline of the glass block using a pencil. Remove the glass block and label the outline as A, B, C, and D. Draw the normal NQM through the mid of AB. Measure 20 degrees with the normal and draw a line through that line. Replace the glass block and erect 2 pins, O1 and O2, on the line. Look through the glass block from the opposite side and observe pins O1 and O2 to be in line. The 2 pins are in line. Place 2 more pins, S1 and S2, on your side so that they appear in line with the O1 and the O2. Both 4 pins appear in line when they are observed the opposite side of the glass block. Remove the glass block and draw a line S1, S2 until it meets the outline of the block. Join the 2 points Q and R. By using a protractor, measure and record the angle R between QR and the normal as R. Record the angle R. The angle R is 13 degrees. Repeat the steps 6 up to 11 for angle I equals to 30, 40, 50, and 60. And tabulate the data including the sine of I, sine R, and the sine I over sine R. Using the obtained data, draw a graph of sine I against sine R. Here is the graph of sine I against sine R, and from there, find the slope of the graph. The slope of the graph is the change of sine I over change of sine R. From the graph, change of sine I is (69 times 10 power negative 2 minus 30 times 10 power negative 2. Divide by change in sine R, which is equal to 45.5 power negative 2 times 10 power negative 2 minus 20 times 10 power negative 2. The slope here is 1.52. Now from the graph, the change in sine I over change in sine R is 1.52, which is equal to the refractive index of the glass used. Sources of error. Parallax vision of images of O1 and O2 and the pins P1 and P2. Parallax readings of angles by using a protractor. The average value of sine I over sine R is a constant number, and this is the refractive index of glass with respect to air.
When the ray of light passes through triangular glass prism, it deviates away from its original path. The angle of deviation is the measure of how much the instant ray of light deviates away from the original direction. Consider this triangular prism ABC. The angle of deviation of light is the measure of how much the instant ray of light deviates away from its original path. The aim of this experiment is to measure the angles of deviation and minimum deviation. Requirements. You have white sheet of paper, triangular glass prism, 4 office pins, 4 optical pins, a protractor, a pencil, ruler, and soft drawing board. Procedures: fix a white sheet of paper on a drawing board by using drawing pins. Place the triangle glass prism, then traces the edges of the glass prism and name as prism A, B, C. By using a ruler, produce a normal just at the midpoint of the point A, B. Make sure the normal is at 90 degrees. The normal should be drawn by dotted lines. This normal is normal M, N. The point where you find 90 degrees is point Q. By using, make a line PQ so that it makes an angle 30 with the normal MNM. This is a protractor. This is 10, 20, 30. This is the incident ray of light PQ. Replace the glass block. Fix 2 optical pins along the line PQ. And later view the images of the pin from the opposite side of the triangular glass prism. Make sure that you are perpendicular to the measurement that you want to take so as to avoid parallax error. And if possible, you can close one eye and use one eye. These images of pins, S1 and this is S2. Then remove the glass block, triangle prism, and the optical pins. Then join points S1 and S2 so as to produce emergent ray. This is emergent ray RS. Then join point QR so as to produce refracted rays. QR is refracted ray. Prolong the line PQ to produce a line PT by using dotted lines. This is point PT. Again, prolong the line RS backward to meet the line PT. From this diagram now, this is angle of incidence and this is the angle of deviation. By using a protractor, you can measure now the magnitude of the angle of deviation. Measure the angle of deviation. By using a protractor, the angle of deviation now is equal to 49 degrees, while the angle of incidence used was 30 degrees. After that, record the observations in the table. The angle of incidence was 30, the angle of deviation was 49. Now you can remove the first white sheet of paper used. Use another plain paper. Fix it in the blackboard, in the softboard. Repeat the same procedures to obtain more results for the angles of 35, 40, 45, 50, and 55. From the results of the experiment, select a suitable scale so as to draw the graph of angle of deviation D against angle of incidence I. From the curve drawn by using free hands, draw the line at the lower part of the curve until when you meet the curve. You can see this is at the angle of deviation 40. It comes to give us the angle of incidence as 40 again. Now we can see that the angle of, or the minimum angle of deviation in our experiment is found to be 40 degrees. As the angle of incidence increases from 30 to 55, the angle of deviation decreases from 49 up to 40, which is minimum deviation, and it starts to increase again. The angle of minimum deviation is the angle formed between the incident ray and the emergent ray when the light passes symmetrically through the prism. And at this moment, the angle of incident is equal to the angle of emergent. Symmetrical condition occurs when line QR is parallel to the base of the prism, that is AC.
The aim of this experiment is to determine the critical angle and total internal reflection of a semicircular glass block. Requirements: semicircular glass block, protector, plain paper, ruler, drawing board, optical pins, and a pencil. Procedure: place a white plain paper on top of the drawing board. Use offset pins to stick it on that drawing board. Take this semicircular glass block and place it at the center of that plain paper. Draw the outline of the semicircular glass block by using a pencil. Remove the semicircular glass prism. Put a mark at the center of the drawing or the outline, and from that use a protector and draw a perpendicular line to bisect the semicircular glass block, and then use a protector. Draw an angle of 20 degrees from point N. Draw an angle of 20 degrees with the line ON, which is normal. Then insert 2 pins on that line and call it P1 and P2. Return the semicircular glass block on that outline. Then view from the other side through the glass block so as to see the images of P1 and P2 to be in straight line. Insert a pin so that they will be in line with the images of P1 and P2. Call it P3. Add another pin so as to be in line with the images of P1 and P2 and pin 3. Remove the semicircular glass block and mark that point of P3 and that of P4. Then remove P3 and P4 and use a ruler to join those points. Use a protractor and measure that angle which is formed by P3 and P4. The angle is 31 degrees. Record the values of angle of incidence and the corresponding angle of refraction. Repeat this procedure for the angle of incidence to be 36. First, you place again the plain paper, the semicircular glass block, and draw around that. Mark a point at the center. Use a protractor and measure a perpendicular line, which will be called normal. Use a ruler to draw that perpendicular line. Again, measure that angle of 36 degrees with the normal. Use a ruler to draw that angle. Insert P1 and P2 make sure that the pins are upright. replace semicircular glass block, and then repeat to view the images of P1 and P2 through that semicircular glass block. While you are looking, you may side in both sides to make sure that there is no parallax. Again, remove the semicircular glass block, name P1, P2, P3, and P4, and remove P3 and P4. Use a ruler, join those pin 3 and 4, measure that angle of refraction. This is 61 degrees. Repeat this process for angle of incidence of 38, 40, 42, and 50. When you complete that, you find that when it is 20, that of refraction is 31, 36, refracted angle is 61, 38, refracted is 67, 40, that of refracted is 76, 42, that refracted is 90, which was parallel to the two medium. And when it was 50, there is no refracted ray. What we get there is that total internal reflection, and that angle was 49. From this experiment, the critical angle for the semicircular glass block used was 41 degrees, where after that, what occurred there is total internal reflection. When light passes from denser medium to less denser medium, it bends away from the normal. When the angle of incidence is greater than critical angle, what occurred there is total internal reflection. Therefore, we can define critical angle as the angle of incidence for a light passing from denser medium to less denser medium, where the angle of refraction is equal to 90 degrees. And the total internal reflection occurs when the angle of incidence is greater than critical angle. When light passes from denser medium to less dense medium, it bends away from the normal if the angle of incidence is smaller than critical angle. When the angle of incidence is greater than critical angle, total internal reflection occurs.
Thermal expansion of liquid. Liquid expands when heated. This fact is observed in a liquid in glass thermometers where the column of the liquid rises as the temperature rises. The aim of this experiment is to demonstrate the apparent expansion of different liquids at the same temperature. Requirements: 3 test tubes of equal volume, 3 capillary tubes of equal diameter, rubber bands, colored water, cooking oil, kerosene, rubber band, loop of thread, hot water bath, and retort stand. Precaution: hot water bath must contain enough water to cover the test tubes. Procedure: fill the test tube with colored water, and cooking oil, and kerosene. Push the capillary tubes of equal diameter through the rubber bands. Push the capillary tube with equal in diameter with rubber bands in each liquid. By using rubber band, keep the test tube together. Make sure that the level of the liquid in the capillary tubes are the same. Place the test tubes in the bath of hot water. Then observe what happens. It is observed that the level of kerosene is higher than the level of cooking oil. Then the last one is water. Conclusion: when different liquids are heated at the same temperature, they expand differently. Compare the expansion of other different liquids. Effect of impurities on boiling point and freezing point of a substance. Introduction. Boiling and freezing temperature of water are used as fixed point in Celsius scale of a thermometer. If water is not pure, it can boil at a temperature greater or less than 100 degrees centigrade, or it can freeze at a temperature below or above 0 degrees centigrade. Impurities alter the boiling and freezing point. The aim of this experiment is to determine the effect of dissolved substance on the boiling point of water. Requirements: thermometer, common salt, water, beaker, chemical balance, masses, and source of heat. Procedure: pour water in the beaker half full. Then heat the water in the beaker until it boils. When water continues heating, measure 5 grams of salt. This is a mass of 5 grams. Measure the salt by using beam balance. This is 5 grams of salt. Again, measure 5 grams of salt. Continue to measure 5 grams of salt until 30 grams and put them separately. The water is now boiling. By using thermometer, measure the temperature of boiling water. The temperature of boiling water is 94 degrees centigrade. After that, add 5 grams of salt. Then continue heating. Record again the temperature of boiling water. The thermometer now is reached at 94.5 degrees centigrade. Add another 5 grams of salt. Then continue heating. Record the boiling point of water before salt is added. It was 94 degrees centigrade. After adding 5 grams of salt, it was at 94.5 degrees centigrade. Record again the temperature. The thermometer reads at 95.1 degrees centigrade. Record again the boiling point. It is 95.1. Continue to add 5 grams of salt until 30 grams have been added, and each time record the boiling point of water in the table. After recording the data, find the rise in boiling point of water by subtracting the value of boiling point when the water was pure from the value of boiling point when the salt was added. From the table of results, plot the graph of rise in boiling point, which is R in degrees centigrade, against mass of the salt added in grams. The nature of graph is straight line, which indicates that as you increase mass of salt, you increase the boiling point of water. Conclusion. Some impurities raise the boiling point of water. Question. Why is the boiling point of water sometimes slightly less than 100 degrees?
When a heat is supplied to a body, a point reaches when the state of the body changes from solid to liquid. The process takes place at a constant temperature. Now the Heat absorbed is known as the latent heat of fusion. Example, ice melts at 0 degrees centigrade, and the naphthalene melts about the temperature of 78 degrees centigrade. Likewise, when a substance cools, its change of state takes place at a constant temperature. In this case, the energy is released out. Aim is to determine the melting point of naphthalene using a cooling curve. Requirements: naphthalene powder, water, spatula, stopwatch, thermometer, test tube, a raker, test tube holder, a beaker, a burner, and a retort stand. Precaution: naphthalene is a hydrocarbon, and when in liquid form, it should not be allowed to touch flames. Procedure: fill the test tube with naphthalene powder. Ensure that 3/4 of the test tube is filled with naphthalene powder. Support the test tube vertically using a retort stand. Fill water in the beaker half its volume. Place a beaker on the source of heat. Lower the test tube filled with naphthalene into the beaker. Heat the beaker until the naphthalene just melts. Set the thermometer into naphthalene liquid. Continue heating until the temperature reaches about 90 degrees centigrade. Stop heating and remove the test tube from the source of heat. test tube and put it into the Leica. Immediately start to record the temperature at the interval of 30 seconds until it reaches 50 degrees centigrade. After 30 seconds, record the temperature. The temperature is 81 degrees centigrade. Continue recording the temperature at the interval of 30 seconds until the temperature reaches 50 degrees centigrade. From the data obtained, now plot a graph of temperature against the time. This is the nature of the graph. Temperature against the time. Now from the data obtained, the graph of temperature against the time is this one. As you see from the graph, from point B to point C, the temperature is constant. This shows that melting point of the naphthalene is the flat part in the graph, which is the temperature about 76 degrees centigrade. From the graph of temperature against time, the melting point is the flat part, which in our graph is indicated from B to C, is about 76 degrees centigrade. Conclusion. Latent heat is the heat required to change a unit mass of a substance from one state to another without change of temperature. From the knowledge you have gained from this experiment, what is the reason behind water pipes in cold countries are usually wrapped in a felt, which is a bad conductor of heat?
The aim of this experiment is to determine the EMF of a cell and internal resistance of that cell. The requirements: we have the ammeter, voltmeter, rheostat, switch, 2 dry cells, and connecting wires. Now we connect all these apparatus as seen in the diagram. Connect as follows. The cell, the positive terminal of a cell will be connected to the positive terminal of an ammeter, and from the negative terminal of the ammeter we connect to the rheostat. This is a rheostat, so we connect. From a rheostat, we connect to the switch. From the switch, back to the negative terminal of a battery, the dry cell. And then connect the voltmeter parallel to the cell, the negative terminal, the negative part,